Okay. So we are starting on 5-1 this week. And 5-1 is on page 289 in your book. So that's what I'm going to put at the top of my paper. So 5-1, page 289. And don't forget to write the date. Today is the 1st. So 11-1-20. All right. So first thing is we are learning about angles of triangles. So interior angles of triangles, this is on page 289 in your book. It says an interior angle of a triangle is the angle at a vertex of a triangle. I feel like you guys have already known this, but anytime you have a corner, it's going to form an angle inside of it. That is an interior angle. So if a triangle has 3 vertices, then it has 3 interior angles as well. So what if you had a quadrilateral that had 6 vertices? How many would you have? 6 interior angles, exactly. Okay, and then it tells us that the sum of the measure of interior angles of a triangle has to add up to 180 degrees. And right there, I actually put the formula for interior angles. So if you have a regular triangle, meaning, any angle or any shape is going to be n minus 2 times 180. So if you had a shape with 6 sides, you would plug 6 in for 2, or 6 in for n. So you'd have 180 times 6 minus 2, so 180 times 4. And that's how many degrees are inside that shape. So our case, a triangle adds up to 180. You guys have already known this. But let's put this in our notes in green at the top. Okay, so for vocab, we're going to put interior angles. The angle made at a vertice, or a vertex. We'll just say vertex. Sorry. Okay, and I'm going to draw a little picture. Okay. Okay. So, and theorem 5-1 is that the sum of all measures of interior angles of a triangle is 180. So I'm actually just going to put in equations in green that interior angles of any shape total is going to be n minus 2 times 180. So in our case, for a triangle, it's 3 minus 2 times 180, so just 180 total. Okay. Okay, we're going to look at example 1. It says, use the triangle angle sum theorem. And it says, find the measure of each numbered angle. So I'm going to draw a picture of this in my notes right there. So I'm going to be drawing it in black. So example 1. And it is page 289. Okay. And it says, find the measure of each numbered angle. Okay. I'm also going to draw my triangle again over here so that I can do work on it. Okay. Okay, and I'm going to switch to red so that we can do our work. Okay, it says that we're trying to apply the triangle sum theorem. So the triangle sum theorem is that one that told us that the triangle interior angles add up to 180 degrees. So that being said, if we know that all of our angles add up to 180, we also know that the angles on a straight line have to add up to what? 180. So it'll be pretty easy to find this number 1 because it has to add up to a straight line with this. So what can we do? Subtract it from 180. So we take, for 1, we're going to do 180 minus 57. And that's going to be 123. Okay. And then for angle 3, how can we find angle 3? But yes, so all of our angles together in this triangle have to add to 180. So angle 3 plus 123 plus 28 should equal 180 degrees. Okay, so we're going to add 123 and 28 together. So that's going to be 151 plus angle 3 is going to equal 180 degrees. And then we can just subtract from the other side. That's going to be 29. So angle 3 is 29 degrees. All right. That is... Does anyone have any questions? Yay? Nay? All right. Okay, moving on. All right, so we also are going to talk about exterior angles. What? We have been over it before. We're just going more in depth. Pretty much the rest of the school year, except for trigonometry, will be stuff that you've already seen before. Trigonometry. No, you got this. All right. Okay, exterior angles of triangles. So an exterior angle is the opposite of an interior angle. So interior is formed at that vertice, and a exterior is formed by continuing any side straight. So this is an exterior angle. Continue this side straight. Oops. Yeah, if we continue this side straight, we would get an exterior angle. Or if we continue this side straight, we would get an exterior angle. And you can do one in either direction. They'll equal the same. So, okay. And the exterior angle of a triangle is formed by one side of the triangle and the extension of an adjacent side. A triangle has 3 exterior angles. So each exterior angle of a triangle has 2 remote interior angles that are not adjacent. So what it's saying is this exterior angle has these 2 remote ones, and they're going to use that with this proof. It says the measure of an exterior angle of a triangle is equal to the sum of the measure of the two remote interior angles. So again, the remote angles are the ones that it is not attached to, okay? So it gives us a proof for this. So the measure of angle A and the measure of angle B equals the measure of angle 1, and that's for this picture over here. So it's saying that this plus this, and then it says we know that ABC is a triangle. That's given. We know that the measure of A, measure of B, and the measure of 2 have to add up to 180 degrees because that's all triangles. Then we can substitute, we're going to start from this side too. So angle 1 and angle 2 have to add up to 180 degrees because they're a linear pair. So that's where they got this stuff. So since they both add up to 180, you can substitute, and then you can have the property of subtraction to get this final thing. So this is actually how somebody built this law, is they proved it with a proof, and then they tried it over and over, and it works. So somebody built this law using a proof. And you will have to do proofs in this. Sorry. Okay, we're going to write exterior angle theorem up in our vocabulary spot. So exterior angles they are created by extending a side past a vertex. And I'm going to draw a little picture of my triangle and then one of my extended sides. Okay, and then up here for exterior angles for my equation, equals my two remote. So the sum of remote interior angles. It's just the two interior angles added together. Okay. We are going to do example 2. All right. And now I'm like, all right, example 2. And that is on page 291. Okay, and it says, this is what example 2 looks like. It says, find the measure of DAB in the front face of this building. So I'm going to draw just the triangle, not, the whole house. You're welcome to draw the house if you want. So find the measure of DAB and we have this cute little triangle house. And this one is 65 degrees. This is 6x minus 4 degrees. And this one, this exterior angle, is 2x plus 7 degrees. And this is D, A, B, and C. All right, now I'm going to rewrite this over here. Find DAB. Okay. Once you start doing your work, make sure you switch to red. All right. So with DAB, that would be this exterior angle right here. Okay, so we are finding DAB, and we know based on our exterior angles theorem that the sum of remote interior angles are equal to the exterior angle. So which two are our remote interior angles? Yes, so they are the interior angles that are unattached to the exterior angle. So 6x plus 4 should be added together with 65 to equal what? Two x plus 7. So again, our DAB should be the sum of angle B plus angle C. All right, so from here it's just algebra. We're going to get all the x's on one side. Oh, first we're going to add our like terms. So we got 6x plus 69 equals 2x plus 7. Okay, and we're going to put all the x's on one side and all the numbers on the other. Oh, this is 12x. I'm so sorry. No wonder it wasn't going to work. I looked in the book. Sorry, everyone. This is 12x, not 2x. Which makes a significant difference here. My bad. Alright, so we want all the x's on one side and all the numbers on the other. So I'm going to take the smaller x from the bigger x, now that we know that this is 12x. Okay, and then we want to put the numbers on the other side. And that'll be 62 equals 6x. And then we just do what to finish this? Divide. So 10.3 is what I got. You got what? Oh my goodness. You know what the book says again? That I wrote right here, but I didn't write over here. This is a minus. I'm just sorry. Dang it. This is turning out to be such a good example. So instead, that would change this to a 61, I believe. And 61 minus 7 would be 54. Thank you. Which will divide evenly, so that's nice. So 54 divided by 6 is 9. Okay, is that what the question asks? It wants us to find angle DAB. So how can we find this? Yes. Plus 7. What you got? 115? Perfect. So angle DAB is 115 degrees. All right. The last thing in this section, 5-1, is called the triangle angle sum corollaries. So a corollary is a theorem with a proof that follows as a direct result as another theorem. We kind of just saw one of those. We saw flow proof. So as with a theorem, a corollary can be used as a reason in a proof. The corollaries below follow directly from the triangle sum theorem. So corollary 5.1 is that acute angles of a right triangle are complementary. Why does this make sense? What do we have in a right triangle? A 90-degree angle. And it says that the acute angles have to be complementary. Why would that be true? Because they wouldn't add up to 90, and since we already know one of them is 90, the other two have to add up to 90, right? What'd you say? Not necessarily, because you could have one as like 62 and one as like 28. They don't have to be equal. All right, there can be at most one right or obtuse angle in a triangle. Why is this true? Right, if we had multiple obtuse or multiple 90-degree angles, that would take up all of our degrees, right? So 180 degrees, if you had two 90 angles, that would take up the whole thing. If you had two angles bigger than 90, that would take up all of the 180 degrees as well. And we have to have 3 angles, so that does not work. Okay, so that being said, example 3. It says, find the angle measure in the right triangles. So this one's going to be fun. All right. So we can either go to a new page or we can just write it below. I'm just going to write mine small below. But all right, so example 3. And that's on page 293. And we are finding the measure of the variables. Okay, and we have a square with a triangle attached to it. Okay, and this is cut into two 90-degree angles here. This is 2x minus 2. This one is x plus 8. This is y. And this is unfortunately 5 over 4 y minus 45. Okay, and I'm going to put it over here. So find x and y. I got my square. This one is 2x minus 2. This one is x plus 8. This triangle is 5 over 4 y minus 45. And this is y. Alright. How are we going to do this? The little one at the top gives you the most information. So we know that since this is a 90-degree angle, what do these two have to add up to? 90. So 5 over 4y minus 45 plus y should give us 90 degrees. Okay. So first thing I'm going to do is combine my y's. And I need to do that by having the same denominator. What denominator? What's the denominator? I mean, there's only one. 4. So we need to make this into 4s. So this is going to be a 4 over 4, right? Because it's just 1. 4 over 4 plus 5 over 4 is 9 over 4y minus 45 equals 90. Now what? Add 45. So we get 9 over 4y equals 135. And then we can multiply by the reciprocal to cancel, right? So we're going to multiply by 4 over 9. So y, I'm going to do my calculator. 135 times 4 divided by 9 is 60 degrees. Okay. And then the other one you said is 30. So we got 60 and 30. Awesome. Okay. Now to find x, we can do the same process, right? All right. I'm not going to do the x. You guys can do it later if you want. Okay. $30 plus 60 equals 90. Plus a 90 degree is 180. Is that what you were asking, Heston? Or are you asking about these ones? Uh-huh. This one? Oh, right here? Well, I don't know. Yes, this would add up to 60, yeah. Which makes this an equilateral triangle, 60, 60, 60. Good. Good point. Okay, we're going to move on to 5-2, which is on page 297. Another one we're covering today and this week, so... Okay, 5-2, congruent triangles. So we've already talked about congruency and about triangles. The principle of superposition, it states that two figures are congruent if and only if there is a rigid motion or a series of rigid motion that maps one figure exactly onto another. So we just learned about rigid transformations. These rigid transformations are translation, rotation, and reflection. And they are called rigid because they keep the same shape and size of something. So superposition just means that we can take one shape and put it on top of the other to make the same figure. So in two congruent polygons, all parts of one polygon are congruent to the corresponding parts or matching parts of the other polygon. These corresponding parts include corresponding angles and corresponding sides. It says two triangles are congruent if and only if their corresponding parts are congruent. So for this, in a proof, you can say CPCTC. That would be corresponding parts of congruent triangles. So if you're looking at it and you're like, hey, all of the angles match up, this is what you would be putting, CPCTC, this. And like I said, this will be a reason in some of your proofs. Okay, example 1, identifying corresponding congruent triangles. We're not going to write this one in your notes. It says, show that polygons are congruent by identifying all the congruent corresponding parts. So, angle B would go with which one? Angle X, because it has the same number of lines, right? Okay, what about side AD? Yes. And then we can match up all the other ones. So essentially what we're saying is each angle matches to another angle, and each side matches to another side. So we can tell that there is a corresponding part for each side and angle, which makes them congruent. So that's what we're doing, is using corresponding parts to prove congruency here. Okay. So we're going to do example 2, but first thing, we're going to, on our notes, write that this is 5-2 at the top, and that it's on page 297. Okay. And in green, I'm just going to put that CPCTC just means corresponding parts of congruent triangles. This can be sides or angles. Okay, so example 2, it says in the diagram, RSV is congruent to TVS. Find the values of X and Y. Okay, so I'm going to draw this. So, and this is example 2. And it is on page 299. So, I'm just going to put the RSV is congruent to TVS. And then it says find X and Y. Ooh, that is a really bad triangle. So we got 2y minus 1. Oh, I should probably put the letters in. R, S, V, and this is 78 degrees. And then we got 24.5. And this is X. And this is 24. Alright, and then I'm going to redraw my triangle over here because my other one was awful. T V S 90 degrees R 2y minus 1 and 78. Oh, 24. Okay, find x and y. Okay. So we need to identify which parts are corresponding. So, if we're wanting to find y, which side on the other triangle corresponds to that? What'd you guys say? VT, that's right. So the straight side of the triangle. So we know that 2y minus 1 should equal 24 because they are congruent. Okay, and we can solve this easily. So 2y equals 25. Divide by 2. Y equals 12.5. Okay, we need to do the same thing for x. So x is here. What would be the corresponding angle of that? R, right? Okay. Do we know R? We could figure it out. How? Okay. Yeah. So if we added them all up, they would be 180 degrees. Or we could just say that we know, since it's a right triangle, we just have to do the other two. And that's going to be 12. So angle R is 12 degrees, which means that if it's the same as x, then what is angle x? Also equal to 12 degrees, right? Okay. Does anyone have any questions on that? Okay. We are going to talk about the third angles theorem. This is on page 299. So the third angles theorem says if two angles of one triangle are congruent to two angles of the second triangle, then the third angle of the triangles have to be congruent. Why does this work? Why does this work? Right. So if we're subtracting from 180 and angle J, and we get something, that's going to happen over here too with the other two congruent triangles. So it has to be the same because they all have to add up to 180. Okay. All right. Some properties of congruence which already heard of, but they're just going over them again. So the reflexive property of triangle congruence just means that ABC is congruent to ABC. I don't know why we have to have this, but reflexive just means identical, okay? So, all right, symmetric property. So this is the one like the law of syllogism, where you have, if you have this, then you know, oh, they're symmetric, meaning you can flip them around. The last one, transitive, is the law of syllogism, sorry, from our deductive reasoning. So these are just flipped. So the symmetric property is just like symmetry. Okay, and then the transitive property. The transitive property is if you have, it's like doing substitution and taking out the middleman, like the law of syllogism. So the triangle ABC is congruent to triangle JKL because they're both congruent to the same thing. Okay. So here is an example of a proof that they do. So what do we know? We know that angle ABD is congruent to CBD because it's given. And we know, or BDC is congruent to BDA. We can see that because they're both 90 degrees. Both are right triangles. Okay, and then the third angle theorem says that if we know two angles, then the third angle has to be congruent, right? And then definition of congruence means that they're equal. And then because of that, we can add them up to 90 degrees, which is what you guys all do in your head because you're like, oh, those are equal to 90 degrees. So they just want to show you the proof of what you actually are putting together logically in your brain. So if we have BCD is equal to 58 degrees, oh wait, sorry, no, BCD is equal to BCD, yes, BAD, or yeah. And BAD is equal to 58 degrees. So then we did 58 minus 90 to get that CBD is 32 degrees. All right, we are going to look at the last proof here. So proving congruence, again, you will have to do this in this section. So proving two things congruent, you can use any of the theorems we've learned or the corollaries that we've learned. So when we're proving two triangles congruent, the first thing we put is all our given information. Remember, this is two-column proof. And this is any proof, right? Our flow proofs start this way. Our paragraph proofs start this way. So JLK is congruent to PLM. That comes from the fact that these are vertical angles. All right. And then we also know that L bisects KM, which means that if it bisects, that it cuts it exactly in half or that the angles are congruent, right? So a segment bisector cuts them exactly in half. That's the definition of segment bisector. And then we go to K is congruent to M. And that's because we already know two of the angles. We know this one and these two. So K and M have to be congruent because of that third angle theorem. Once we've proved all the angles are congruent, then the triangles have to be congruent. Okay, does anyone have any questions on that? Like I said, we will be doing proofs again. Sorry. Okay, that's all I have for you guys today.